I guess it's time to start. So my name is Honza Hubička, and I would like to speak about recent improvements in AutoFDO. The AutoFDO was in GCC for a while, like 11 years, but it was mostly sleeping, as you will see. So this is the joint work with Dhruv and Kugan from NVIDIA, and Petr from SUSE. Andy Klein is formerly from Intel, previously from SUSE. I'm not sure, and Eugene is from Microsoft. I will start with a short overview. What's the profile GCC? So basically, we can think of three profiles we are handling. The first thing is the CFG profile. So we have the control flow graph, and we annotate it with expected branch probabilities and expected execution counts, which is used for optimizations, like deciding where to spill your register or do other things. We have a call graph profile, which is basically the same thing, but on the function level. So we have expected function execution counts and expected call side execution counts. And we also have the value profile, which lets you to annotate statements or values in the program with some additional information. So we do the indirect call targets. We do some ordering of the functions. We are measuring which function was executed at the beginning of the program. And there is a typo because I was working until 5 a.m. on these slides. So there will be many typos. It was out of my control, but there was no other day to do it than tonight. So there is expected alignments for sizes for string operations, and we also measure some funny things, like we are deciding if the division always happens by power of 2, which makes it much easier than if it's not power of 2. And there is an old paper from 23 years ago, which we made as a students on this project. And basically, you have three ways how to get profile into GCC. The first thing is that you use the instrumentation. So you can use the profile generate. The profile generate will add some counters into the program and will measure all these data precisely. The problem is that it has visible costs in the runtime. So I measured it on the Clang binary because I use it as a benchmark for some of the tests for this talk. And it's like 50% of extra runtime, which might be a problem because your program will be too slow to operate. It also has code size costs because you have to add all these increments everywhere. And it has, it's producing a lot of data. So if your program is running just for a short time, like GCC or Clang does, each time it streams a lot of files, and it takes time. The other thing is that you need additional runtime, so it's sort of hard to set it up like in the kernel environment or some embedded setup, even though there's a support for that, which was practically used. So what it does, it works very well on the single-threaded programs because that's easy to calculate by counters. If you have multi-threaded programs, you might deal with the race conditions. And the race conditions are not that bad because they don't happen that often, but I have seen that they have sometimes extreme performance impact, like making your program 200 times slower because all the CPUs are clashing on the single counter all the time, which practically happens, if your program has a hotspot. The other problem is that the profiles are specific to your build setup, so you cannot save your profile and use it on other computer very safely because likely something changed, like little details in the header and the profile will not read. And we also do not implement any context sensitivity, so there's a path profiling or context-sensitive profiling, but that's not implemented. So this is all based on this very old paper from '94. By Bala and Larus, and it works relatively well in practice. Like in SUSE, we use it to build quite a few packages. The main problem, at least for SUSE, is the reproducibility. So it's sort of hard to get the builds reproducible, but if it works, it makes your programs noticeably faster. So if you don't have a profile feedback, you can still use the profile. So there's a static profile, which is done by kind of set of heuristics. The heuristics are basically dividing branches to the loop and non-loop branches. So the loop branches are easy to predict because for programs to be slow, the loops has to be looping. So average loop is looping dynamically. And it is pretty good because it gets like 88% of success rate out of 88 possible because the branches are not always fully determined, taken or not taken. The rest of the branches are predicted by some big heuristics, like that the opcode values are usually positive. People doesn't like negative numbers. And that works like 72% out of 85. And there are some branches which we have no idea because we have no heuristic matching it. And altogether, it gets like 73% out of possible 86 on spec 2017, which looks pretty good, actually. I don't know, like when I first saw these numbers in the paper 23 years ago, I was sort of surprised it's even possible to do it by such primitive measures. But it's sort of good on identifying hot paths in the functions because you have good chance that the branches you guessed are the good ones. What is also good on is guessing the relative frequencies of the basic blocks. So for example, if you want to do spell code placement, it's not that bad on it. Because basically it guesses correctly that if code is inside of the loop, it's likely to be hot. If it's outside of the loop, it's likely to be cold. That's not such a big magic. And what it's not able to do, it doesn't do any value profiles. Theoretically, it can be done by value range propagation, but we don't do. And also, it's not good on answering things like what's the expected count of iterations of the loop. And that's something like vectorizer is interested in, because if the loop is iterating usually 3 times, it's not a good target for vectorization. An average loop in the spec is actually iterating like 3.7 times. But we have to make the educated guess that the loops which matters iterates more. So we still optimize them. And also, we don't do any interprocedural profiles, even though there is a follow-up paper. This is based on the Ball and Larus paper from '93. There is a follow-up paper which is claiming that this is also useful to determine hot functions in the program. I never implemented it because I don't think it's realistic. Like, we have too many indirect calls, too many calls to library. Real-world programs are not closed. You cannot analyze every single call in it. So I don't think it's going to be very effective on that. And I have never seen compiler implementing it correctly. So the AutoFDO is kind of the compromise of this somewhere in between the normal FDO and the guest profile. So the basic idea is to use the perf to record the low overhead profile. And there is this LBR and BRB extensions, which lets you to basically record with every sample. It records a sequence of jumps which was taken just before executing the sample. And that gets you pretty good data, how the program is behaving. Once you have the overhead profile, you can use a debug info to get information about the expected execution counts of the statements. And that's used by GCC to optimize. So what's the main selling point is that you don't have very big runtime overhead for profiling. So you can keep your perf running and you can profile in the production environment, and from time to time you can rebuild. It's maybe easier to set up. My experience is it's much harder to set up. But once it works, it's easier, I guess. And the other thing is that the profiles are actually less sensitive to the environment because they are sort of easily annotated to the source code. So you can ship them with your program and use them with different build details like headers, and they will likely work reasonably well. So that's something which I think might be useful, for example, to get reproducible builds for packages which cannot be reproducibly trained. We can just ship this type of data if it works well enough. So it's one of the motivations to work on this feature. So there's a history of this feature. It was contributed by Google in 2014. And this was, again, there's a paper on it from 2016, which is by Dehao Chen and David Xingling Li. And it's listing what kind of benefits they get at the time they was contributing it to GCC. And it actually looks really good because it's comparing the normal profile feedback with instrumentation profile to the AutoFDO. And the paper is claiming that on the average, you get actually better improvement for AutoFDO than for normal FDO, which is suspicious. But it is explained in the paper. It is saying that the AutoFDO actually is kind of context sensitive. It's creating every inline function differently. And in that case, it has the advantage over the usual FDO. And also the numbers are sort of as you would expect. The programs with complicated control flow like Perl or GCC or Xalang, which is a parser of XLS, are improving more, and the programs with simple control flow are improving less. So this was contributed. At that time, it was clear that Google is switching to LLVM, so I sort of thought it's a useful feature, and I thought that I will finish it after it will be submitted to GCC, so I accepted the patch. And then it was bit rotting. So I found that I don't have any computer where I can run it, because at that time it was requiring Intel CPU, and I had my boxes was AMD. So nothing happened. I gave up on looking up for the machine which would run it reliably. In 2016, Andeklin came, and he contributed some improvements. So he added the auto profile bootstrap, which is useful for testing. And also he added test suite, which is kind of very useful thing to have because it was not tested at all. So I tried to use it again, but I found that I need a specific old version of perf and very strange tools from Google Git, and I gave up again. And I still needed an Intel machine, which I didn't have. So it's very hard to get the Intel machine. And in 2017, I decided that I should do something, and I worked on the rewrite of the profile representation in GCC. So the problem was at that time, the profile representation was basically implemented twice. Once for the static profile, which was frequencies and probabilities, and once for the measured profile, which was counts. And this was the third profile which didn't fit to either of these two categories. So I decided that I will do some C++ magic, and I will implement the single data type which will hold everything, and it will be easy to operate. And it was a lot of work. So for a full year, I was basically rewriting the profile code in GCC. And I didn't get to AutoFDO because it was still not working for me. So in 2018, Bincheng appeared, and he started to do some bug fixes. He was working for Alibaba, so I thought that maybe he will get AutoFDO working, but then he stopped working on it, so bit rotting happened again. And then Eugene Rosenfield from Microsoft came, and he started to fix AutoFDO, which made me happy. And I think the steering committee was also happy because he was appointed as a maintainer of AutoFDO. So after like 7 years, the code started to be maintained. And what happened in 2025, I noticed that for 3 years, I already have the machine which is able to run AutoFDO. So I was happy, and NVIDIA started to submitting patches, which was sort of hard to review for me because I already forgot what the code is doing. So I decided it's time to start seriously fixing it. So I will explain you what AutoFDO is doing internally. I have developed this very sophisticated test case, which is very stupid. It has 2 loops. One loop is calling a function, and the other loop is inside of the function is increasing value in the array. So it's a very stupid test. And you can compile it with AutoFDO. So you need to use, I have a pointer, you need to use -G because you need the debug info to read the profile back. And you need to have the test running for long enough time. This is actually not long enough to get good data. And then you need to use this very magic perf command line, which I will explain. So the perf command line is basically enabling recording of taken branches. So I don't want to have a record about time which is spent in the basic block. I want to know how many times it was executed. So the taken branches are closer to what I'm measuring. And then you need to enable this LBR profiling, which is -B. And if your CPU doesn't support it, you get an error. And then you need to set up a reasonable counts, which is -C. It's better to be prime, even though Andy claims it should be prime -1. I don't know. So what happens is that if you run it, you can read the profile into perf, and you can see what happens. And this is what you get. So you get 74 samples. Okay. How do I get back? Yeah. So you get 74 samples for this initial move, which is loading the address of the array. Here is the loop. And all the instructions in the loop gets this 94,000 samples, and the return gets 106 samples, which is not completely precise, but if you divide these two numbers, it's roughly roughly 1,000, so it's not that bad. It's sort of estimating that the loop is iterating 1,200 times instead of 1,000 times. And this information can be processed into the form which GCC understands. And here is a problem. You need to use the AutoFDO tools. And at least on the SUSE box, they are very difficult to build because they depend on LVM. They depend on a lot of Google ecosystem like libprotobuf. And this libprotobuf is changing the APIs every release. So every release, each time I upgrade my box, I have to recompile it. I have to fix some compilation errors. And I have to live with that. So this is a problematic moment. Then you run it, and it's a very interesting tool, So basically what you do, you give it the binary because it needs the debug info. You give it the version, which is a magic number. There is only 2 versions, so this version 2. You give it the measured profile, and you give it what it should provide. And it outputs a lot of messages, like full screen of messages. Sometimes it's like false. It's okay, you don't need to be afraid of these messages. They mean nothing. Yeah, I don't know how they manage to get so many messages, but it's sort of, I think it chases away the users. So if you get past this, you can actually read the profile which was produced. So this is dumb Chekhov, which is a very nice name because we have Chekhov -2, and you have here the Chekhov is on the end, and this underscore, which is like different naming conventions. And this is what's inside of the profile. So there are 2 functions, test and main. This is the total number of samples in the function, so you can identify how hot the function is. This is the number of executions, basically, the head executions of the count. And these numbers are actual line numbers. So these are line numbers starting from the beginning of the function. It's done this way because you want to be stable across small source code changes. So if your function moves in the file, these numbers doesn't change because it's relative to the beginning of the function. And it's basically saying that this number 1, the beginning of the function is executing 74 times. 2.1 is this test of I. So this is 2.0, this is 2.1, this is 2.2. Those are discriminators. And it's executing 91,000 times. Line number 3 is the increment. It's again executing 91,000 times. So line number 4 is the return, which is 105. So this is the information which GCC reads. And this is also the information which you can ship with your program. And it would be useful for the optimization. And so what's interesting about this profile is that it is actually recorded in inline instances. So here I have removed the non-inline attribute. I replaced it by static. So the test is inline into the main. And this is the profile of the main. Here are the lines of the main, which it thinks they are executed 0 times, which is wrong. And here it is the inline version of the test. So you still see the loop. But you don't see the rest of the test function because that's sort of distributed into the outer loop, which is executed 83 times. So that's the context sensitivity which the profile has. Okay, so the next step is that you need to run GCC again, and you can give it this auto-profile file, which was generated by Chekhov. And I have added a warning auto-profile, which lets you to figure out if the profile is obviously broken. And also you can look into these 2 dumps. There are 2 passes handling the file. So it's sort of interesting to see what's inside of them. Okay, so what happens inside of GCC? So first there is a new pass which is called AutoFDO offline. And AutoFDO offline is basically first reading the profile into memory, which is already a problem because if you have the full profile of Clang, you read into memory like 30 megabytes of data. The second thing is that it is stripping the symbols because GCC is introducing some suffixes of the functions at the late compilation, so it takes them away. As a result, it gets duplicated appearances of the functions. It's removing all the functions which are not defined in the current unit because it doesn't have any use for it. And it's doing this offlining. So if the inline instance is cross-module inlined, it takes it as offline. And it gets some partial information what the inline function is doing. And it also merging the multiple instances together because you get a lot of duplicated functions, like if the function was inline many times out of your unit. So this is So this is what it does. So the second step is inlining. And in the inlining, basically, we are using this, this context-sensitive information. So even before building the profile of the function, if this function is called enough times, so this total number is big, we will inline it, and we will do it early. So that's actually improving the code because we are early inlining already quite big functions, and we are relying on the test run to have sane inlining decisions. You know, if you build a test binary which has inlined 1 megabyte function, we will inline 1 megabyte function, and we will be very slow. So this is the first optimization that happens, and then GCC is also matching. I should have put this on the slide before. It's also matching the internal representation with the profile data. So this is actually the dump of the offline pass. And here you see the Gimple representation of the loop. And here you see the line information. So those are the different lines. And here you see the execution counts which are stored in the profile. So you can see that this basic block is executed 74 times. This basic block is executed 91,000 times. This basic block doesn't have any information. The reason is that IVOps has removed the original induction variable and replaced it by different one. And I moved the debug info around, so the basic block is lost. And the return is executed 105 times. So I added this because I think it's easier to kind of compare what's going on and understand what happens. And then after inlining, there is a profile inference pass, which is basically trying to determine the CFG profile out of the data it has. So because it doesn't have all the data, so it's done in a couple passes. So this is the control flow graph of the loop, the entry block, the conditional of the loop, the main body of the loop, and the return. And basically here it is looking up the counts of the individual basic blocks. So it's able to find the entry block, which is basic block number 2. It's able to find this block, which is basic block number 3. It doesn't find this block. It doesn't find this block because there's a bug. You know, we lose the location information somewhere during the early optimizations. I will have to fix it. I noticed that tonight, so there was no time to debug it. And so this is the first step. So it has these counts. It doesn't have the edge probabilities, and it doesn't have information on this basic block. So in the next step, it is trying to determine the counts of edges as using the Kirchhoff laws. So, you know, the number of counts coming to the basic block should also leave it. And that means that if you know, for example, okay, a lot of, yeah. So if you know the count of this basic block, you also know the count of this edge because it's only one. So this is basically what it is doing here. And eventually it's able to determine the count of this basic block because it's the sum of this edge, and both of them are known. So the missing information is filled in this case. It doesn't happen always, but here it happens. And if it doesn't happen, you know, it's filling up the profile based on the information which is there. Now here there is a one basic block missing, which is the exit basic block. So basically it finds that the basic block should be executed the expected number of time and fills the missing data. This actually happens in practice quite often. You know, if you have the bigger block which is optimized away, you have no info at all, and you need to somehow fill these missing fragments from somewhere. So this is also a new feature which I added, but I checked and VM is doing exactly the same. So I guess it's a reasonable way how to do it. And at the end of the day, you get the profile. So here you can see the frequency of the entry block is 1. The frequency of the loop is 1,236, which is almost 1,000. And the frequency of the return block is 1. There's information that it was measured by AutoFDO. It's not profile feedback, it's not guessed. And it's also having full information about the edge probabilities, which is the optimal outcome. So, you know, in more complex test cases, this looks much worse. So this is what happens. And after this, the idea is that the compiler can continue as if it had the normal profile, and it should work pretty well. Also I added a new feature. You know, what you can do, you can also generate a real profile. You can measure it, and then you can compare the two profiles. So it's able to tell you that the profile measured by AutoFDO is sort of okay, but a little bit wrong. So it's basically saying, if I scale the AutoFDO profile to match in the hottest basic block, then the cold basic block is miscounted by 19%. So that's accounting for this extra 20% of measurement error I had in my profile. So I think this is sort of useful. If your program is not behaving fast enough, you measure the real profile, you compare it, you check where the broken profile is, you fix it, and GCC improves. That's the idea. I did it successfully a couple of times, but it's still work, which is waiting for me. Mm-hmm.
Can it write out a profile from this?
So
basically,
mm-hmm.
You have the AutoFDO and the real one.
Mm-hmm.
Can't you write out an AutoFDO one?
Yeah, I was thinking of it. Yeah, that's easy to implement. It's not done. But I think it would be meaningful because then you can ship your real profile with your application, and you can get. So that's on my to-do list. Thank you. That's a good comment. And so to show you how well it works, I added this. This is the thing you need to add into your specs if you want to measure with auto profile. Again, it's a lot of extra blah blah blah, but it's done, so you can cut and paste it from the slide. And this is what happens with GCC 15. So I made all the numbers relative to the trunk without any profile feedback. So 100 is the trunk with no profile feedback. The blue bars are no profile feedback GCC 15. So overall, GCC 15 is just like 1% slower than the trunk at the moment for me. And if you look on the AutoFDO, it's actually like 15% worse than if you don't use any profile feedback. And if you use the FDO, the real profile, it's actually 2% better than if you have the no profile feedback. So this is not good because we are not improving the performance. So that's where we started, like at the beginning of the summer. And actually, I got suspicious about the Google numbers, so I decided to measure them. So I compiled the Google bench, and it sort of works. So here, the Google branch is like 21% worse than trunk today. It's 14 years old compiler, or 11 years old compiler. If you enable the AutoFDO, it improves by a little bit over 1%. Sorry for the numbers, but it was 4 a.m. and I got depressed by Google Sheets. And if you use the profile feedback, you get another 1%. So the AutoFDO is not better than real FDO, but it is somewhere in between, and it's closer to FDO than no FDO. The difference is smaller because I think I'm using several CPU, which has a lot of cache, and the CPU 2017 is very small for the current machines. So the benefits would be better if I used a smaller, like desktop machine. But I think this is sort of okay. I also measured the data yesterday, so you can see the things has improved. So now with FDO we are like 2% faster. With AutoFDO we are like 2.5% worse, which is less than 20% or 15%. So it has improved. But the goal is that it is definitely, this bar should improve for the release. So there's like 3% to go. And that's the good news. As I was preparing the slides, I found overflow, integer overflow. I fixed it, and it improved by over 1%. So another 2 days, and the problem is solved.
I was going to say, if you look at the previous one, the slide all the way back to the one compared to 15, the two big ones are his X264 and Exchange.
Yeah. I know.
50%, 50%.
Yeah.
And now they're only 9. Now it's
exactly. There's a reason for it. Like the Exchange has fairly complicated cloning, which needs to happen. And if the profile says, you shouldn't clone here, the performance goes out of the window. The problem with the Exchange is also open back report is that it needs, it's turning off the vectorizer. We measured that the loop is iterating a few times, which is less than the vectorization count. And the vectorizer gives up, but it is still beneficial because the epilogue is faster than the original loop. So Richard should fix it. Right, and then the numbers will be fine. So there's actually something to look at. There are a couple of benchmarks which are slightly worse with profile feedback than without, and that should be fixed. But overall, I hope this is not a disaster anymore. And in 2 days or 3 days, it will be fixed completely. So these last 2% are always easy, right? And yeah. So actually, there is an argument. I checked what LVM is doing because LVM has AutoFDO actively supported by 3 different teams for 10 years. And so the LVM is overall like 93% of our performance. And it's 93.45, 93.58 with the AutoFDO, and 94.2 with the real feedback. So yeah, it's behaving like expected, but the difference for the profile feedback is smaller than for us. Again, like this is all normalized to the GCC with low profile feedback. So I wanted to make a joke that LVM is better on compiling GCC than we are, but it's not true. Because with profile feedback, we are also improving like by 9%. So LVM is not better GCC compiler than GCC. There is an argument that spec is not a good test case for this because spec is by now very small. This is really designed for the big applications. So one of the biggest applications I have on the hard drive is LVM. So I decided to try to build LVM with different settings. And this is the numbers I got. So this is size, this is performance. Everything is again normalized to the trunk without FDO. Everything is built with O3. And LTO, I use the thin LTO for LVM. So if you use the AutoFDO, the performance gets like 40% smaller, which is very good. The performance improves, but just very little. But there is no regression anymore. If you use FDO, then the binary is slightly bigger, but the performance is actually fastest. So GCC is better on compiling LVM than LVM, which is good news.
This is lower is better.
Yeah, lower is yeah. This is size. This is time. And yeah, so it's the other way than the previous slides. So yeah, thank you. And this is compared to LVM. So the LVM is actually building itself slightly better than GCC built LVM, which actually that's why I'm using LVM as a test case because it's quite complex code, and I expect them to be optimizing for them and not for us. So if we perform well, it means that the optimization is sort of robust. The AutoFDO is actually making the binaries much bigger than, but also faster. And FDO this is a surprise to me that didn't happen in the previous in LVM 20. They actually implemented the size optimization for code, which wasn't there for many years. So they improved quite a bit, but still the performance is slightly worse than if you use GCC to build LVM. So I think the outcome for me is that before GCC 16 is released, I would definitely like this performance be closer to this. So there's something I need to analyze and figure out why it's there, but it's already sort of turning to be useful. It's not useless optimization anymore. Okay, so that's how it works. And I have 10 minutes to explain what was done. So what was changed since GCC 15? There was test suite support, which was done by NVIDIA, which I'm very happy for because the test suite is necessary. The stripping of the late suffixes. So previously we were simply losing the profile for all these suffixes. So if you don't have a profile, things doesn't work very well. I added the offline pass, which is helping LTO because when the AutoFDO was contributed, LTO didn't exist. The problem is that then everything which is cross-module inline, which is a lot of functions, doesn't get a profile. So that was a big problem. I have rewritten this profile inference algorithm, so added the scaling and fixed quite a few bugs inside. And the thing which makes me crazy is handling of zeros in AutoFDO profile, because as you have seen, the 0 is not the real 0. 0 just means that there are not enough samples. And we do a lot of multiplications, like where we inline function, we multiply its frequency by the frequency of the call site. If the frequency is 0, we forget everything. So I had to add a lot of special cases about AutoFDO zeros, which are really annoying. So I actually found that LVM is doing the other way around. They just change the zeros to non-zeros by some heuristics. So that might be less ugly way how to do it. But for the start, I just fixed the main problems. We also added scaling of the AutoFDO profile up, so there is no row-tough errors because the numbers are very small, and if you do integer arithmetic or you do it badly. And we added this comparison, and we added this discriminator as rewrite because the path was simply broken. No path profiling is broken. I will fix it. And we also added the regular testing on LNT, so I hope this will sort of ensure that things doesn't bit rot again. Because at least we get some statistics about the performance. So what's still being worked? One thing is what we don't have, and LVM has, is called this hierarchical discriminator support. So basically, LVM is encoding a triple inside of every number, which is the discriminator, which is used to discriminate the statements on the same line. And copy ID, which is used when you make the multiple copies of the statement. Each of them get different copy ID, so we can make the difference between multiple instructions executing one copy of the statement and instruction executing 2 copies of the statement, which is not visible in the debug info at the moment. And multiplicity is used for vectorization, instead of executing it once, it's executed 8 times. So if this is implemented, I think we will get significantly better profiles of the vectorized loops. And if I look on the performance regressions, the vectorized loops are the main problem because the code is changing enough, so we simply get completely broken code on the loop header, and we think that loop is executing once, and we disable optimization on it later. So the other thing is that at the moment, dwarf2 out is not saving linkage names of inline functions. So inline functions get the dwarf names, which are not unique, and they are pretty ugly, so this is something which needs to be fixed. It makes dwarf slightly bigger, but not much bigger. So that's, I think, I want to discuss with Jakub if it is feasible to do by default. Actually, LVM is having option, is having -f debug for profiling, which is disabling some optimizations and adding discriminators. We might have also options.
So that's for functions declared inline, right?
No. If you have function which is only inlined, the debug info doesn't have its original symbol name. It only has a dwarf name.
Also not in the abstract project.
No, it's not there simply. Yeah, it's missing.
Okay.
It's one liner patch to dwarf2 out. It's very easy to add, but it's simply not there. So
I think it shouldn't be that big problem, especially when you merge strings.
Yeah.
If you inline it 1,000 times, it will
Yeah.
be there.
Yeah, it's not clear to me if you want to enable everything by default. Like the discriminators are enabled by default, and I think no one was using them in these 12 years. So I can enable this by default, but there's option to have at least one command line. We can discuss if it should be on or off by default. Also, LVM is having special option, which is -g line numbers only, which is disabling all the rest of the debug info. It's adding only stuff necessary for AutoFDO to work.
Isn't G1 enough for that?
No, G1 is still bigger than what LVM does because it has types. This doesn't output types, which is a lot of data.
There was a proposal long back to have one that was like G-line number only.
Yeah. So LVM has it. It works. It's not hard to implement. We can do it. So the other thing is that, for example, the IP split is not handled correctly because the offline encode doesn't understand it, and it will kill the call. So that needs to be fixed. And also the auto profile bootstrap, I have some patches for, but no one is reviewing them, and I don't feel confident with the build machinery. So maybe I will just commit them and see what happens. So the other thing is that this AutoFDO tool is pretty broken. So I had this missing line information about the one basic block, and it happens because there are 2 statements which are assigned to single address. The thing is only able to do the first one. So I added multi-line support, but the problem is that the dwarf is able to represent multiple lines per single address, but not multiple inline stacks. So if you have the C++ and you have some iterators, you often have multiple inline stacks by single statement. And that's another thing which I think needs to be added somehow. And that's a bigger surgery to the dwarf. So the other thing is that we need to switch to 64-bit to get the hierarchical discriminators supported. And we need to do something with the symbol name clashes. If you have two static symbols of the same name, they will get merged together, which is not a good idea. It was like that for 10 years. LVM has a flag which is called -f unique linkage names. And it adds random suffixes to every static function, which is ugly solution. So NVIDIA folks did support for saving the file names, which I think is more useful. If you look what LVM folks are doing, they have 3 different implementations of this, and they are adding some extra sections to do it. But I think it can be done by dwarf. So I hope this can be fixed. And so what needs to be done? By GCC 16, I really hope this can be declared to be useful, because otherwise it will fall to disrepair again. So the code should be better than without FDO, and should be close to FDO. What also I need to do, the data structures which are holding the profile are very bad. So if you are, for example, compiling Clang, you can see that it's really compiling slowly, because it takes time to load the data and forget it. And it's using the default STD maps, so those are B3s, and B3s are slow. The other thing is that we need to do something with the dwarf, or we can do the alternative routes which LVM is taken, which are called pseudo probes, which are sitting in the special sections that are basically duplicating dwarf with some extensions. And I think we want to do the magic with our tool and forget this finally named merge profile measurer, which is crashing if you run it without command line option. And I think we need to rewrite the tool. So I have looked, and to my surprise, actually LVM has already done it. There's a LVM prof tool which is installed with every LVM, and it's able to do the same job. And it's something like 1,500 lines of code. But it's using some LVM infrastructure. But it looks it's possible to rewrite it, or it's possible to read the same format as LVM does, but the files will not be compatible because the discriminators are different. So I think it would be confusing if we had a file which can be read by both tools. So I would vote towards writing the great Chekhov, but I don't want to be the one doing it. So here's the option to make me really happy. And I have 2 minutes, so I think there's a, let's see. No, this is actually the end of the slides, because I fell asleep. So this is the current state of AutoFDO, and I wonder if there are any questions.
So for the zero frequencies, wouldn't it be trivial to just interpret zeros as ones?
Yeah, well, I was playing with it. The problem is that if you interpret zeros at once, then the GCC doesn't handle it happily either, because it thinks that all the profile is broken because you have multiple edges out, all of them with one profile, and so on. So what LVM does is that it's at the end of this profile inference, it's identifying this what they call islands of the profile which is non-zero. They find the shortest path to the entry of the function, and they make it 1, which is also a great hack. So that's the alternative thing to do, but then you inline. And this situation goes away, because you have function with a full zero profile, you inline function with non-zero profile, you have to do something. So yeah, I'm undecided what to do here. I tried to simply fix all the occurrences where zero happens, and there are many. It's not pretty. So I will maybe try the other paths like LVM did. Mm-hmm.
Testing. If I understood correctly, when you are reading AutoFDO profile, the counts get associated to the source lines.
Mm-hmm.
And what happens if you have, let's say, a C++ template which can be expanded into something that executes
Many things.
a lot, or can execute even very, very different code based on the data type. What happens there?
That's what these discriminators are doing. So each time you have the function, and you have multiple statements with the same line number, the statements get different discriminator numbers. So those are these dot numbers like .1, .2, .3. So we are able to distinguish them inside every function uniquely.
Well, you also have the Mangle name too.
Yeah. So we have 4 templates, but if things are inlined, you only have these discriminators. And that's also, these numbers will not match the LVM numbers, unless we implement exactly the same code gain as a Clang, which would be some work. So that's why the profiles will not be compatible between the 2 compilers because of this.
Yeah, I mean, presumably the simple approach for fixing these zeros is simply to propagate counts directly down the CFG from the entries that dominate the zeroed entries. If you've got a dominator which is 100,000, then the zero can't actually be 0. It must be at least 100,000. Maybe divided by the number of places that are known to inline it or something like that. But it was better than 1.
Yeah, the inference algorithm has something like that. It's basically identifying the equivalent basic blocks. Like this basic block will have the same count as this basic block, which is like the basic blocks around the loop. And it's taking the maximum number out of these 2 numbers. So it's doing that.
Enough, right?
It works sometimes. So like the main problem is if you inline, you have the function which got no samples at all, and you inline it with the function which got some samples. The question is what to do. So at the moment, I simply inline the function with non-zero profile. I make the outer function to have 0 profile. So I end up with the island of non-zero code inside, which happens much later.
You can't propagate backwards,
Yeah. So we will need to do something.
So how much work is left? Right. How much work is left now, do you think? How much time before normal users can use it?
It's easy, just the last 3%. We have seen it, right?
Yeah. But it's still
I
quite
think
a bit of work.
LVM has active support for 10 years. They do produce a lot of little hacks. I think we will end up doing something similar if this is taken seriously, and I think it's sort of worthwhile to take it seriously. But I think like for GCC 16,
16 already.
So if we fix the bugs, we will get reasonable numbers. I'm mostly worried about this tool. Like convincing people to use the tool is very tough because the tool is very shaky.
Right.
Look very, very dangerous. But I definitely want GCC 16 to have useful AutoFDO. Not perfect, but useful.
Hey, Onza, it's a good talk. So my question is, like, other than spec, what other real workloads are you planning to test?
Well, at the moment, I'm testing Clang, GCC, and specs. I didn't put GCC numbers because it was too late. But they look sort of similar to Clang. The differences are smaller. Like Clang is improving by over 20% by profile feedback, which is crazy. GCC improves by like 7%. So it's the same story, but compressed.
You're getting, at the low level, you're getting information. At the low level, you're getting information about branches. Are you able to get any information about jumps through function pointers?
I didn't speak about it, but the format is actually saving the common destinations of indirect jumps. So it's able to do indirect call profiling.
Because I was basically thinking, could this capture devirtualization of C++ code?
Should help X264.
No, because for some reason the virtualization doesn't help on this particular machine. We tried it. It's happening actually, but it's not helping. So the other thing is that there are these binary optimizers, Propeller and Bolt. I didn't put numbers there, but I got them running. What's interesting, Propeller is able to use some extra counters, like how predictable branch is, and I think that will be useful to have to eventually once this is working well enough, which at the moment it's not. So I have time, things to do. Okay, I guess we need to go for a coffee, otherwise it will be drunk before we get there. So thank you.